Okay, so we're going to start with the sixth lecture in M269, and today our topic will be mainly on the heap, and then we talk about the heap sort. This is, as you remember in our last meeting, actually we talk about multiple algorithms that are well known in the field of sorting. And the last one was the heap, and we said at that time that we're going to cover it in our next meeting. The structure is totally different. We are going to deal with trees instead of the regular linear structures. So heap is an array, but it can be visualized as a binary tree in terms of the organization. So heap is a tree. This is what I want you to know, and it is actually a binary tree, not only a tree. It's a binary tree where, if you remember, the node or the root has maximum, or the parent has maximum of 2 child. So it can have 2, 1, or none child. When it is a none child, something like this, it has no child, then it means we are at the leaf level. So these like 2, 4, and 1 are leaves in this tree. We have actually one property in the heap trees, which is the max heap. Max heap means the node, which is the parent, must be greater than, or must have values which is greater than the children. So as you can see here, for example, this root 16, the children are 14 and 10. So 16 is bigger than both 14 and 10. 14 is parent for 8 and 7, and it is bigger than them. 10 is bigger than 9 and 3. 8 is bigger than 2 and 4, and 7 is bigger than 1. And that is the max heap property. Okay? So that is the root of the tree, which is the first element, as you can see here in the array. We want to see, this is the visualization of the heap tree, but how it looks in memory. In memory, it is like this. It is 16, the first element. Then we go to the left node, which is 14, and then 10 on the right side, number 3, and then we go back again to the left side. We have the 8, see, number 4, and then the right side, which is 7. Then we go to the second level, or second half of the tree, we have the 9 in the same level, and then 3, and then 2, 4, and 1. So here is the 10 elements. This is how the elements are going to be stored in the array, and this is how we visualize the element in the heap tree. Okay. Please clarify your question, Lama. Yes, these are just number examples. These are just numbers. You can put any number there, yes. Of course, if you put 15 and 7, but here 15 will work. In this side, 15 will work, but 7 here doesn't work because 7 is smaller than 9. So it will not work. If you put here 15, it will work because it will not violate the property, the max heap property. 15 will work here, so become 8 and 7, which is greater than 8 and 7. But if you put 7 here, 7 is smaller than 9. So this is a violation of the heap tree, which is the max heap tree. Which 9 you mean? This 9? No, these are just examples. The content of the tree, the items here are just examples. No fixed values. The fixed values are these element, the index of the element, like this one at index 1, index 2, index 3, index 4, 5, 6, 7, 8, 9, 10, which is actually represent the indices here, the indices of the array. Yeah, of course. We will come to this point, Lama. We will come to the point. No, also Abdullah. Even if you want, if at some point you have 7 here, 9 here, 3 here, then this is a violation. But to fix this issue, we have something that we need to do, which is called the max-heapify. The max-heapify. And this one actually, it's very important because it corrects the single violation of the heap property. So if there is a violation in one of the node, the function max-heapify will help us to resolve and correct this problem. So we have some of the operations. We have the build max heap, which is going to produce for us a max heap tree, or from an ordered array. If you have a single violation in one of the nodes, then you can apply the max-heapify, and you have the insert, extract max, and heap sort. This is an example. If you see here, you have the node 16, which has two child, 4 and 10, and here we have a correct order of the nodes. But when it comes to node number 2, it has the value 4, and 4 is smaller than both 14 and 7. I want you to note something as well. The left side of the tree of the child must have a value that is bigger than the value on the right side. See, 9 is bigger than 3. 14 is bigger than 7. So here we have a violation. That is another, by the way, this is another type of the trees, that the one I'm talking about just now. Now, yes, Lama? See here. If element AI violates the max heap property, correct the violation by trickling elements down the tree. You got? So we have to bring the element that is violating the rule down to the bottom of the tree. It's not necessary to be in the last element. It might be somewhere in the middle. This is how we are going to see how it works. No, I said in some trees, in other trees, Lama, not this trees. In other tree, we have the right side is bigger than the left side, not this type of tree. Okay, now let's see how it works, how the max-heapify will correct the error. Now the error in 4 is smaller than both 14 and 7. Now what to do? We call the function max-heapify A2. The array is A at index number 2. Now, in this case, the 4, we have to exchange the A2 with A4 to the left side. And then we have what? Now we have the exchange between 4 and 14. Now 14 will go up and 4 will go down. See, 14 is down, 4 is down, and 14 is up. Now, still we have an error. 4 is bigger than 2, but it is smaller than 8. So in this question is here. Now we have 4, 14, and 7. Let's go back to the first case. 4, 14, 7. Why we choose to replace 4 by 14, not 4 by 7? This is a question to answer Rawan's query. No, it is because 14 is bigger than 7. So if you want to replace a value 4, you want to replace it by either 14 or 7, you must replace it with the bigger. So that's why we choose 14. You got it, Rawan? So you have 4, 14, 7. We have to choose one of them to replace the 4 with. So we choose 14 because 14 is bigger than 7. So 4, 14, switch or exchange. So 14 will go up, 4 is here. Now 4 is bigger than 2, correct, but it is smaller than 8. So again, call the function max-heapify. A4. We have error. So A4 was going to be exchanged with 9. So with A9. So 4 will go down to the 9, 8, and 8 will go to the 4. So we have the new tree, which is 8, 4. If you look at the tree now, it is max heap tree. So we have 16, 14, 10, correct. 10 is bigger than 9, 3, correct. 14 is bigger than 8, 7, correct. 8 is bigger than 2, 4, correct. 7 bigger than 1, correct. The time needed to max-heapify any tree is O of log n. Why? Because it's actually a division. No need to go through all item. Every time I go only half the way, half of the paths. Right now what we are doing is just fixing the error, correcting the error of the tree, and that's called the max-heapify. We are not sorting. If you look at the tree here in this array, it is not sorted. See, 16, 4, 10, it's not sorted. Even after you max-heapify, we are not sorting the array. We are just fixing the error. The process of sorting using max-heap, it's coming later or the next. Exchange A2 with A4. You mean here? A2 and 4. No override. It's called exchange. I didn't get your question, Abdullah. What do you mean by override? Not override, it is exchange, because you are swapping values. Yeah, it's called... No. The term override, it's not suitable for this process. Simply, it is just an exchange. Okay, good. Now, building max heap, how to build a heap from the array using max heap function. The max heap function actually, it will convert the array of n elements to a heap max this way. So build the max heap of A for all element I up to n, from n divided by 2 down to 1. Do max-heapify. AI means for all items from the half of the tree, from here, backward down to number 1, because he's number 1, max-heapify. Why they do this? Because all the other nodes below or greater than n divided by 2 are what? Are leaves. They are leaves. يعني here احنا see Now we are starting from I equal n divided by 2, which is here, back to 1. Any item n divided by 2 plus 1, any leaf n divided by 2 plus 1 onward is what? They are leaves. So you don't need to max-heapify all the values. All what you need to do is to max-heapify the values from n divided by 2 down to 1. So the time taken actually to do this, because its division is going to be divided log n, and then this process, the log n, need to be applied n times. So the complexity is n log n. طيب روان، الآن احنا لنعمل عملية البيلدينج الماكس هيبيفاي لازم نعمل ماكس هيبيفاي، يعني to build a max heap لازم نطبق عليها الماكس هيبيفاي اللي اخذناها من شوي على كل element لحتى نضمن انه هو يعني we are satisfying the max heap property. طب لحتى نعمل هذا الشيء لازم نعمله على النودز. احنا ما في داعي نعمله على كل النودز، بكفي نعمله على النودز اللي هم البيرنتس اللي إلهم تشايلد. فانت لو تيجي تجربيها ارسمي انت، حطي ايتمز لحالك ان array elements وشوفي اقسم الان على 2، حتلاقي انه كل الان على 2 من بعدها هم leaves، كلهم ما إلهم ولا تشايلد، هم هذا اخر صف. اي شيء من ان على 2 وفوق للواحد حيكون هو nodes parents إلهم child. So that's why I will start from this point and apply max-heapify on every single node. انت لو عملتي الماكس-heapify على هذا التري، على هاي الليف، احنا شو حنستفيد؟ There is no point because they have no child. Okay, great. No, see, it is log n because you are going to what? You are going to multiple path, صح? We have multiple path log n. But for every item you need to max-heapify. So you are going to apply it n times. So if you have for example 5 elements, you have 5 max-heapify call for this function. Okay, so this is a demo for building max heap using the build max heap function. So this is an array, this is the A. Now we say max heapify. Of course, if you have this array, now you have it, you have to reflect it visually. So initially it will be like this: 4 1 3 2 16 9 10 14 8 7. I did not get your question, مشاعل أو مشعل. لا we start from up here. مشاعل. Okay مشاعل, I did not get your question. إيش يعني 1 16 17؟ والله يعني you make me confused now more. I did not, still cannot see these numbers. What do you mean by 1 16 7? Do you mean this in the circle? طيب wait let me, yeah, this is the third step. Wait, let me go through the process step by step. Now let me explain how we draw this tree. We draw this tree starting from the first element in the array, which is 4. So 4 will be here. And then 1 will go to the left. 3 will go to the right. Then go again to the left side. 1. It has 2 child. 2 and 16. See, 2 and 16. Then the 3 has 9 and 10. So 9 and 10. Then we finish this level, go down. The 2 has 2 child, 14 and 8. So 14 and 8, and the last child go to 7. We start filling up the nodes from left to right. Is this one clear now? This is how we visualize the elements in the heap tree or the max heap. Second step is to maxify the heap maxify, because we need to fix the error. What error do we have here? See, we have 4, which is bigger than 1 and 3, correct. 1, which is smaller than 2 and smaller than 16. Then we have to max-heapify here, this element. What else? What else we have problems? 3 is, yes, 3 is what? Is bigger, smaller than 9 and 10. So we have to apply max-heapify here. 3. Type. Can we apply in other position down? No, we cannot. Okay. But we cannot apply now because the problem might be fixed later. So let's start by maxifying or max-heapify one by one. Because fixing one problem somewhere might fix the problems in other levels. This is how it works. So, now what should we do next? Starting from this node, 1 has a problem, right? So 1 with 2 and 1 with 16. Which one is bigger? 1 with 16, right? Correct. So what we do here is to swap. We swap this, but we swap it with what? Yani this one, we swap it with 16. Type. Okay. Type. There is something missing here. See, back again to this function. Can you see something in this definition? Here, this code. Can you see something? أيوة مالها الآن على 2. Okay, what's up? What's about the n by 2? What's the problem with this? Yani, what is your note? أيوة طيب yes محمد عاطف. What do you mean by this? We are building the max heap from n by 2, right? Here, here down, or we should start here. أيوة. So we should fix the problem first. This is the last level, so we should start working on this level. Backward, up, here, up. So the first problem is with this leaf, 2. 2 is actually smaller than 14 and 8. So, and here the second one, 16, is bigger than 7, so this is okay. So we have problem with the 2 and 14. So maxify this node. So 2 will be 14 and 14 will be 2. Swap. Swapping 4 with 8. And this is what you can see here. See? No, not 1. Swapping now 14 with 2. So the 2 become down here. See now? And 14 become the parent. Now we fix the first problem with this level. And we fix the problem with this level. Now let's go up to the second level. This level, 2 parents. We have the 1 and 3. Let's fix the right one. You can start with any if you want. It doesn't matter. So 3 is a bit smaller than 9 and 10. Swap 3 with the 10. Position 3 with position 7. A3 with A7. So 10 will go up and 3 will go down. So the new one is 10, 3, 9. Correct. Now back to 1 here. 1 is smaller than 16 and smaller than 14. So maxify. So 1 will go where? 16, because 16 is bigger. So 16 here. Again, swap again, because 1 is again less than 7. So 2 swaps with this Max-heapify. 2 swap. Because the 1 cannot fit here, it fit the last node. So 1 will replace 16, and then the 1 will replace 7. So the last node will be like this: 16, 7, 1. Are we done? Okay, I think Amal is the one who's more focusing. Not done yet. We said we continue up to reach 1. This is 1. Still have violation. Good. Good, Tabi. Good. We have 4, right? We have the 4. 4 is still violating the root. We said we go from the half of the trees up to the root. Root is violating. So where should the root go? 4 with 10? Are you sure? 16. 16. Yes, correct. So 4 is going to be replaced by 16 for 1, replaced with 2, but 2 does not fit here. Again, another swap. Where does it going to be swapped? 16, 4, he doesn't fit with 4, right? So here we have, see, 16 go up, and 4 go down. Again, we need to make another swap. 4 will go down because 14 is bigger, so 14 will go up, and 4 will go down. Again, the 4 is smaller than 8, so we'll replace 8 by 4. So the new 4 will be here. Yes, correct. Excellent. I think all of you got this issue cleared, right? Okay, ممتاز. لا, we cannot from yes خطوات من تحت لفوق, صح. Yes, this is the only way. Yes, يا لما. This is the only way that we need to follow the structure of the heap sort. Four by 10. What do you mean by 4 by 10? And from swap from which point? I go back slide or here? طيب, which line? Which step? This step? Here? Okay, here is the parent 4. You want to swap it with 10? Yeah, Lama. If you swap it with 10, then 10 will go up here, and 10 is smaller than 16. So you have violation more. I think you're not focusing today. Okay, no problem. And this is actually how we are analyzing the performance. So overall, the process of building max heap is O of n. This is the complexity. Actually, it's O of n because here, when it comes to finding the total work, amount of work that is needed for the loop, actually we have the loop here, right? See the loop? The loop is going to from n divided by 2 into 1, right? So here the total amount of work in the for loop, see, in the for loop will go from n divided by 2 to 1. And every time we have to call the function max-heapify. So the max-heapify, we say the max-heapify will take a complexity of log n. صح? Log n. Okay. And how many times does it have to be applied? And every time we call the function max-heapify. Okay. Yes, okay, n times. But here, if you look at the example, we are starting from n divided by 2. If you want to find the real amount of or the exact amount of work, every time you go from one node to the other nodes, we are dividing n by 2 to the power n. So if n is 1, so 2 to the power 1 is 2, then 2 to the power of 2, 2 to the power 3. So it is 1, 4, 8, 16, until you reach the root, which take log and c. So by doing, this is a mathematical equations, by replacing the n divided by 4, assume that it is equal to 2 to the power k, then replace 2 to the power k by every n. So we have c, which is of course multiplied by 1, c 2 to the power k, 1 2 to the power 0 plus, just replace it here. Every time just replace 2 to the power k by n. Divided by 4. And then you will get k plus 1 divided by 2 to the power k. Abdullah, this is a bit confusing when it comes to mathematical proofs. But it's just showing you here how much work is done inside the build max heap. It actually include two types of works. It go through the loops for every single node, and then we call the max-heapify. And inside the max-heapify, we have multiple steps. The max-heapify, as you could see here, it perform multiple swap, right? Not only one single swap. It reach to number of swaps. It might reach to n number of swaps. That's why we cannot say that the max-heapify here, it cannot take log n only, because sometimes it reach up to the leaves. So the total amount is O of n. That's what is the mathematical operations tell us, the mathematical proofs. Now till this point we did not get to the sort, how the heap sort work. All what we did is just to build a heap tree and find or max-heapify the tree to correct the errors. Now let's work on implementing the heap sort. The heap sort has a strategy for sorting. First, build the max heap from an ordered tree array. What is the minimum element in the array? Specify it. Swap the element an and ai. Now the max element is the end of the tree. So if let's say the minimum is 1, you keep swapping the number until you reach the bigger number on the end of the array. We will come to more explanation. Then discard the node from the list, from the heap, the one that we already passed and visited and already stored in the array, and a new root going to be examined. If it is violating the rule of the tree, then you need to max-heapify and then go back to step number 2 and continue. Now with the example that we are going to take, we will make things easier. So this is the original array, which include 10 items, and this is how we visualize it using the way we described just now. This is just visualizing the tree. Now how the heap sort works. First, now we have 16 as the top, right? This is the top, and there is no violation here. This is a heap tree, a max heap. Since the root has the largest value, replace the root by the leaf, the last one, the last element. So the last element, remember, the array has from 1 to 10. So the last element is 10. So replace 1 by 10. After that, 1 will go up, and 16 here, number 10, 16 will be out of the tree. So this is going to be the first element in the tree, 16, in the array, in the sorted array. Now, what do we have? We have a violation. So 1, now we have 9 elements. See, heap size started with 10, now it's 9. Why? Because we take out 1 node from the tree. Now we have to max-heapify, because 1 is smaller than 14 and 10. So do the max-heapify, you will reach to this point. Of course, 1 with 14, right? Then you have 14, 1 here. Then you have the 7 with 8, 1 with 8, and then 1 with 4. So this is the new tree after max-heapify A1. Now the new tree here, this one, is not violating the rules, the max heap, because 14 is the largest value. So replace 14 with, no 10 now, with 9, because no 10 time, no 10 elements, with 9. Number 10 is already out. Replace it with 9. So 1 will go up again, and 14 will be here. Take out the 14 from the heap. So 16, 14. Now the size of the new heap is what? Is 8. So it has 8 elements. Again, max-heapify 1, A1. So 1 will go to this direction now, right? To the 10 here, because 10 is bigger. So 10 will be here, 1 will be here. Max-heapify. Of course, we do what? Swap first. 10 with 8, because the maximum is 8. So 10 will be here, 2 will be up, take out 10 from the 3. So 16, 14, 10. Now 2 is up, max-heapify. So 2 will go to this direction, 9, because 9 is bigger. And then we'll go to replace the 3. So we'll have 9 here, 3 here, 2 here. Then replace it with 7, because 7 is the last element. And then take it out. So 9. We continue doing this till the last element of the heap. The complexity of the heap sort is n log n. Like which algorithm? Like the merge, right? Both of merge sort and heap sort takes log n. And they are considered the most efficient sorting algorithm. And this is the code in Python. As you can see, both of the heap and the merge sort are both of n or log n complexity in their worst case. Please try to go back again later and go through these recorded classes and try to do it by yourself in order to make sure that you are really understanding the procedures and the structures. Any questions? Yes, Lama. I'm not sure if they ask you for showing the steps. let me check it, please. Lama, send me the question by email, and I will check it again. I will get back to you. I'll just make sure that it's a clear answer. Regardless how many marks they are assigning on this question, but let's make things clear. So I will check the question and get back to you. What do you mean, Ya Abdullah, discuss TMA? If you have specific issue, Abdullah, in any of the questions, please send me your question by email and I will get back to you. I didn't go through all the question, but maybe like what your colleague just now said, some of the things or question are related to meetings which have not been covered yet. So that's why sometimes you need to wait. Regarding the submission deadline, it's going to be on somewhere around 4 or 5 or 6 of July. So I think you have maybe 3 weeks. No, not yet, Abdul Hakim, not yet. Okay. Let's take a break, 2 minutes exactly, and then get back. Okay, you ready now? Okay, that's good. Now let's back to the recursion and the complexity analysis of the recursive function. This is similar to what we have started in the previous two meetings, where we are going to analyze the complexity of a given function which works in recursive way. So as you can see here, we have the function fn equal the summation of fi multiplied by fi minus 1 for all values of n greater than 1, where fn equal f1 and both of them equal 2. So the process will stop. I think your friend Abdul Hakim has a problem with the sound. Okay. So the problem is here, or sorry, the problem or the function will stop when the value of f0 and f1 equal 2, and then the function will stop. So there is no more decrease in the value of I once we reach 1 or 0. So both of them will reach to value 2. Now we want to show how this recursive will have a exponential complexity. How this function will have an exponential complexity. So in order to understand how this function is going to be analyzed, if you can see here, the function is going to be executed twice, one with the value of n and one of n minus 1. So if let's say you have the function f5, f5 is going to be executed as f4 and f3. fn will be of n4, the first value, and then 3. And this is now another fn. So fn4 will be fn3 and 3 minus 1. 3 will be 2 and 2 minus 1. 2 will be 1 and 1 minus 1. And 2 will be 1 and 1 minus 1, and so on, until you reach 1 or 0. See? This is the stopping condition. When we reach 0 or 1, we stop. As long, here you see, we stop at 1. As long as we didn't reach f1 or f0, you have to continue breaking the number into two numbers, or the function into two functions. So why this is called recursive? Because once we reach to this point, we will start executing backward the function until we reach the node. Now we want to prove that this function has an exponential complexity. Later we come to the code, Abdullah. Now what we want is to prove that this function has an exponential complexity. Now let's consider this function. Okay, the one we are describing now. And to solve the problem, we need to deal with this function as a Tn. So now let me switch to the whiteboard. Can you see the whiteboard now? So this is the original function. Let me copy it for you. This is the original function. Now, let me type here. Now, this is the Tn. So the Tn equal, since you have the summation for all the values here, so Tn equal the summation of Ti plus summation of Ti minus 1 plus summation of C. And this is actually for all values I equal 1, n minus 1, n minus 1, n minus 1, 1, I equal 1, I equal 1. Now this is lead to the summation of every Ti is actually equal to summation of Ti plus T of 0 plus the summation of Ti minus 1 in term of n, it is actually the summation of Ti minus Tn minus 1 for the value of n. And for the summation of C, it's going to be plus C of n minus 1. Yes. So if you can see here, we have one Ti here and one Ti here. So in total, it is what? 2 summation of T of I minus, we have here Tn minus 1 minus Tn minus 1. We have Cn minus 1 here plus Cn minus 1 plus T0. Clear up to here? This is how we reach to this equation. Yes, because 1 minus 1, yes. Okay, that's great. Now we move to the second part. Let me open. Sonia, you just enter the class now. Like which part you did not get exactly? Okay, here what we did in this question here, we found that we have Ti from here, Ti plus T0 because n minus 1, which is 1 minus 1 is 0. And then we have summation of Ti minus Tn minus 1, and then C of n minus 1. In the last one, the last equation, here we have one summation of Ti, and here is another one summation of Ti. So in total, we have two summation of Ti. And then I minus Tn minus 1 here, I bring it here. Then the C n minus 1, I bring it here. And the last one is T of 0. This is how I build the first part of the equation. Now, moving on, starting from this again, let me write it for you. T we have Tn equal to summation of Ti minus T n minus 1 plus Cn minus 1. Of course, we don't care about the T0 because it's 1. Next is, because this is for Tn, next is to deduce the Tn from Tn minus 1. Let's find Tn minus 1. What is Tn minus 1? Tn minus 1 equal to Ti minus Tn minus 2 plus Cn minus 2. This is how we find Tn minus 1. What we want is to do now is to find Tn minus Tn minus 1. Tn minus Tn minus 1. Just substitute the value that you can see here. Yes. So it's equal to 2 Ti. Let me just make it nicer. Okay, like this is better. 2 Ti minus Tn minus 1 plus Cn minus 1. I'm talking about this part, huh? Here, I'm talking about this part. Which summation? No, خلاص. Nothing about the summation. We are dealing with the function itself now, in terms of Tn. So this is the first one, right? Minus Tn minus 1, n minus 1, which is this part. 2 Ti. I don't know why I put this. Wait, please. Here, no need for the arrows. So 2 Ti plus t n minus 2 plus c n minus 2. So we have here, let me change the color so you make it clearer for you. I can take out these two with this two because they are minus. Yes. Yes, because minus with minus become true, here it's minus, right? And then when I apply the minus, because I say here's minus, so minus with minus become plus. And here it was yes, it was plus with the minus become minus. Don't forget that what I'm doing is subtraction. So the minus plus become plus and the plus become minus in the second half. Yes, it's here. Hey. Yes. This is the minus Cn2. Cn minus 2. Remove it with what? No, you cannot remove it. This is Cn minus 2 and this is Cn minus 1. How can you remove the two different arguments or numbers? If both of them minus 1 or minus 2, yes, you can do this. No. Wait. We are going to clarify this as well, Abdullah. Now we reach to this point. We are taking these two elements, minus 2ti, minus 2ti, and we are left with tn minus 1 plus and cn minus 1 plus tn minus 2 minus cn minus 2. Now what to do is to find tn. See, now this answer, let me open another page. So starting from this point, t, we say that at the end tn minus tn minus 1 equal to tn minus 1 plus cn minus 1 plus tn minus 2 minus cn minus 2, right? Next step is to find only tn. Oh, yes, minus. Yes, minus, correct, Lama. Yes, minus. Thank you for the correction. Now, we need to find only tn. So, in order to find tn only, you have to move this part to the second part of the equation. So, tn equal, this one minus tn will become plus. So, equal tn minus 1 minus tn minus 1 plus cn minus 1 plus tn minus 2 minus cn minus 2. So this one and this one will be removed. So in total tn equal to cn minus 1 plus t n minus 2 minus c n minus, sorry, let me just change. It's because I have in the screen here. Minus c and minus 2. Right. Now, if you look at this example here, now we reach to two parts of the question. We have, yes, now I'm coming to this point. We have this, yes, Abdullah, yes. You are correct. Now we have Tn minus 2, which is now a function. And we have the C, which come with the C as a constant, right? These are constants. C is just a constant. So in terms of functions, these are actually going to be considered as, both of them as C. We can just call them C1. We can call them C1 because we don't care about how much time is going to be multiplied with C. It's just a factor of constant number. So we can consider it as Tn minus 2 minus C, call it C1 for example. Is it clear? C is just a constant. Lama, C is just a constant. So if let's say you just consider it, if you want to consider C as a common factor between n minus 1 and n minus 2, let me find it here for you. So we have it, here we have C, n minus 1 minus C, n minus 2. So if you have it in general, if you have the C, okay, you got it? Type. Abdullah did not get it. Explain it, Yarama, since you got it. And you stopped me from continuing the explanation. Exactly. So this C is a common between this C and n minus 1 and n minus 2. So it will be n minus 1 with n minus 2 for both C's. But we did not continue, but you stop at this point only. Why you don't just open the brackets? So it will be C n minus 1 minus n plus 2. So n with minus n will go. Minus 2 plus 2 equal 1. C1. Yes. Yes, yes, can, yes. Which one here? This slide or the previous? Okay. Which one, ya Abdullah? Which TN here? Last here? Okay, this is the TN. This is the TN. So TN here. This is the last value of TN. TN equal TN minus 2 minus C1. Why we did not put it in the equation here, you mean? No, Abdullah, hi, this slide, I just want to show you how C1 is found here in this slide, the last element. How here? How we find this C1? I explained this here in this slide. That's it. Okay. Now, let me back to the slide. Just give me please 1 minute. I just need to answer the call. Okay, sorry for the interruption. Okay, now after explaining how we reach to this point, put the cursor. now we have, after we find, this is the 2 for sigma ti, and then minus tn minus 1 plus cn minus 1. This is what I've just explained just now. And then we find the tn minus 1 equal, this is actually for the minus 1 of the t. And then we minus tn minus 1 from t of n. Then we have 2t n minus 1 minus tn minus 1 plus tn minus 2, which is this one, plus c. And I show you how we found the c using assuming that c is a common factor between the two equations, and then the tn will equal to 2tn minus 1, this one, plus here we have actually tn minus 1 plus tn minus 2 plus c. So here what we do, we have to make an assumption. We will assume that the effort that we are taking in finding tn minus 1 is similar to the effort we are using for finding tn minus 2. So we will consider them, both of them, as tn minus 2. So we will say that 2tn minus 1, this one, plus tn minus 2 plus c. So we are assuming here, we have to make assumptions. So sometimes in solving mathematical problems, you need to make some assumptions in order to simplify the equations. So this is one of the assumptions that we are going to use in order to find or to simplify the questions. So here, since we assume that the effort we are taking in tn minus 2 is similar to tn minus 1, so we can also include here this tn minus 2 to this tn minus 1. So we can say that we have 3tn minus 1, because we said in our assumption n minus 2 equal n minus 1. So since we have here 2tn minus 1 and here we have 1tn minus 2, so we can consider them both as 3n minus 1. And this is what we can see here in the upper bound calculation. Again, we reach to this point where we have minus tn minus 1 plus tn minus 2. So here we can make assumption. What is our assumption? Assumption is n minus 1 equal n minus 2. The effort we are spending on n minus 1 or finding n minus 1 equal to the same effort we are spending on n minus 2. So in this case, we can say that this one and this one, both of them n minus 2 or n minus 1, whatever you want. So we come up with this equation. Since we have again this assumption, we can also say that this is actually 3tn minus 1 plus c. Somebody said, no, I want to use the n minus 2. No problem. You can say n minus 2 plus c. So the upper bound is 3tn equal 3tn minus 1 plus c. So if you want to go down, one level down, to find the tn minus 1, then minus 1 from the original n minus 1, it will become 3tn minus 2. So what is the tn minus 2? Tn minus 2 equal 3tn minus 3. So tn equal 3 multiplied by 3tn minus 2 plus c plus c. If you continue doing this for multiple of n's, you will reach to 3 multiplied by 3 of tn minus 3 plus c plus c plus c, and so on until you reach the stopping condition, which is t2. And the last one is t2, because after t2 you will reach t1 and t0, as you can see here in this function, 0 and 1. So the last operation will be applied on t2, right? So after n minus 2 steps, you will have this complexity, o to the power 3 to the power n. Why? Because it is repeated 3 times. Every time it is 3 to the power n. Okay, what is the lower bound? The lower bound, when it is 2tn minus 1. This is the lower bound. 2t of n minus 1 plus c. Here, if you want to find again, the similar to what steps we followed here, minus 1 from n, so n minus 1 equal 2 multiplied by t to n minus 2, and then the tn minus 2 equal 2 and tn minus 3. So the same thing, 2 multiplied by 2 for the function tn minus 2 plus c plus c. How you found this? Just replace the value. So tn equal, just replace the value of tn minus 2. And then we have this function, which is going after reaching t2, going to have a complexity 2 to the power n instead of 3 to the power n. So the complexity is always exponential. Either it is 2 to the power n or 3 to the power n in maximum. Maximum is 3 to the power n. And minimum is 2 to the power n. Here, to find this value here, to reach to this point, you need to do a substitution. Substitute the value of tn minus 2 here, and then substitute the value of tn minus 1 here. Then you will reach to this operation. You want me to show you how we reach it, or it's clear? Okay, looks like clear. So this is the pseudocode. This is the pseudocode of the function. This is the direct recursive function. If n equals 0 or n equal 1, then return 2. So this is f. This is when f 0, and this is for f1, return 2. And then you have the for loop from 1 to n minus 1. Every time you find the sum plus fi multiplied by fi minus 1. This is just the pseudocode of the recursive method. Now, what is the second question, B? In B, they were asking, explain how, by not recomputing the same fi value twice, one can obtain an algorithm of n to the power 2, n square. How can we make this code work in n square without recomputing the value of f twice? See, here what you can see in this example, let me explain it. In this code, in the for loop, sum equal fi multiplied by f minus I. So this is to find the first sum. Now in the second round, what will happen? It will be fi minus 1 multiplied by fi minus 2. So the idea is here, why you already calculated fi minus 1 here. So you should think of a way that this fi, since it's already computed here, no need to compute it again. No need to calculate fi minus 1 in the next round, since it's already calculated in the previous round. If you manage to do this in the code, then you can minimize the complexity of the algorithm. So can you see here what's going on? So ti equal ti plus tk, this is the fi. Previously calculated, so don't need to calculate it again. Multiply by tk k minus 1. So here, if you manage to do this, then the for loop, the two for loop will create a complexity of n square. So here 2 to the power n, and here n square, which is much better. You got it? It's clear? So here the concept here, to minimize it, we use the memory to store the already calculated value. In the last example, or the last question, give an algorithm for this problem that only use O of n. So it must be much better than what we have reached to. Okay, how to do this? It's actually to find a formula to compute Ti in terms of Ti minus 1. So how can we find Ti from Ti minus 1? So here we need only one for loop in this example, which will go n time. And from here we find Ti equal Ti minus 1 plus Ti minus 1 multiplied by Ti minus 2. So what I do, I derived the value of Ti minus 1 from the previous value. So in the next I, so Ti minus 1 will equal to Ti minus 2 plus Ti minus 2 multiplied by Ti minus 3. So it is deriving the value or computing the value of Ti based on the value of Ti minus 1. If you do this, we are actually executing this process n time. So the complexity is O of n. So what is the point of what we are saying here? The point is that the same problem can be solved using 3 different techniques. One of them takes 2 to the power n, the second take n to the power 2, and the third took n. So how smart you can build your system to be much efficient with less complexity. I hope that, and this is actually a reference for the famous recursive recurrence formulas and what is their big O notation. You can also memorize it. I hope that it is clear for all of you. Actually, I do understand that it is a tough lecture. Now, don't worry, I stopped the recording. Now you can, or I can say that it is a tough lecture where so many mathematical proofs. Now I can see multiple attendees are writing, means you have something to say. But before you start writing and continue writing, it is not required from you to memorize all these proofs. What we need is to understand how things are going on. You are not a mathematician. You will not be asked to write codes in this way. We just help you to analyze the complexity of algorithms somehow based on some mathematical proofs. It's very important to at least go through it, because you are, as a computer science, you need to understand how your algorithm, later you are going to write some codes. Somebody need to analyze your code in order to know whether your solution is sufficient or efficient or not. As you can see also, when we talk about the sorting algorithm, the best one, the fastest and the best in terms of complexity was the merge sort and the heap sort, which took n log n. So if you know this, if you know the weaknesses of the existing algorithm, you might design in the future one sorting algorithm which take maybe log n or n, and you become very famous. So that's why it's important to go through such analysis, even though it's tough. But if you go through my class again, if you go to the links that are available in the on the slide itself, for these parts we have extra links that are supportive links. Go through it. It will help you a lot to become familiar with this or such kind of analysis. Now feel free to talk. Even it is the longest lecture for today. طيب, it's good to end your day and maybe your week with this class. And again, I would like to just confirm with all of you that if you have any question regarding the specific points in your TMA, you can always send me the question. Please don't send me the question number. Send me the question body itself and what is the issue, and then I will reply you as soon as possible, inshallah. I think somebody is writing, but I cannot see. By the way, I'm sorry because I couldn't see what you have written starting from long time ago. I don't know why the cursor was up. That's why I said nobody's writing. طيب, I cannot go up very high. طيب, download the books. The book, I think there is a online version of the book, right? Rawan. Yes, Abdul Hakim. Yes, sure, you can leave. The deadline for the TMAs, it's supposed to be the first 4 days of July. You will receive the announcement very soon, and you will be notified about the date exactly. And check the GCC, check the central LMS, please. Please send me email. If you couldn't find the book somewhere, I will try to help you. I don't know where exactly is located. I will check with you. العتيبي, I think you need to wait for the official announcement regarding the deadline, submission deadline, because I think it's updated somehow. Please check, for the book, please check the central LMS page, and I think you can download the book from there. The material is available there as well. Okay, thank you so much for your attendance, and I will see you on next week, inshallah. Yes, Fatima, go ahead, please. Yes, what's the question, Fatima? فاطمة, البروجكت الفصل الماضي يس تم مش إلغاؤه, تم اعتماده مع الريبورت. يعني في البارتس فقط اللي مش موجودة في الريبورت هي اللي اعتمدت. درجة جمعت مع درجة الريبورت كاملة. يس. الله يعافيكم يا رب. طيب, شكرا. شكرا لكم. أيوة تفضل يا خلود. يس. نعم نعم. المشروع التخرج annual course اللي بتنزله الفصل الأول A، الفصل الثاني لازم مباشرة بعده B باستثناء السمر. يعني إذا نزلت بروجكت A على سبرينج، البي بيكون على الفول مش بالسمر، فهو annual course. ما في، لا ما في السمر، ما فيه مشروع تخرج. درجة السورس كود الامبلمنتيشن في عندنا درجة أخذت على مش على السورس كود، الامبلمنتيشن والبرزنتيشن فيه درجات المشروع التخرج. تاريخ it will be announced soon. The deadlines for the TMAs it will be announced soon. Please wait for my announcement on LMS. طيب thank you and see you next week إن شاء الله. السلام عليكم.